Hi everyone, my name is Christian Lazaro and I'm a senior bioengineering student at the University of Maryland. And today we're going to be talking about two groups of units that we learned in class and how those units pertain to a real world structure and pretty much the machine that constructed it. So without further ado, let's get started. Okay, so jumping in, the topics we'll actually be going over today, or rather the units involved in today's calculations, are stress/safety factor, material properties, rotational forces, and pulleys. Now, the real-world bits we'll actually be relating these to are the incredibly massive Burj Khalifa and possibly the most important machine involved in its creation, the tower crane. The Burj Khalifa is actually really huge. It's the tallest building in the world and it actually stands at about 828 meters. And that is some grade A penny dropping height right there. But anyway, it's made primarily from a dense, high-performance concrete known as C80 and consists of about 160 floors and a spire which is pretty much all broken up into 27 tiers like a big Arabian wedding cake, which you can pretty much see on the right. And its design is actually known as the buttress core model, which is pretty much a model where it has 3 arms and a big hexagon at the center. But knowing all this information and its height and everything, the question I really want to know is, how is it able to withstand its own weight just because it's so massive? Now, to figure this out, it's going to get a bit crazy, but we're going to have to delve into the units on material properties and stress/safety factor. Essentially, if we can determine the stress the entire building exerts with its weight and use that alongside the stress of the C80 concrete, or strength of the C80 concrete, we can find the safety factor and prove the building's ability to support itself. However, this requires some simplifications, so the C80 concrete is special and therefore its strength and density can be assumed to be of the highest caliber capable by that material, since we're not really given it anywhere, at least on the internet as far as I can find. And since that's the case, additionally, since this building has a lot of weird shapes throughout it, the base and tier 0 will have to be broken down into simpler shapes to find their areas using the Google Maps distance measure that's pictured on the right, with the area of each layer after tier 0 being reduced by an additional 3.6% just because this kind of yielded an area closest to the real world area of the tip of the building just by the end of the calculations. Additionally, the spire tiers will be considered equal length simply because we can't calculate the lengths just because every other tier that's not part of the spire can be calculated with its length just using the length of the floors. Now, using an online source for said floors, it was actually found that floor 154 was at a height of 584.5 meters, which means that a floor is about 3.79 meters, and that can be used to calculate the tiered lengths of all the tiers, which again has to be done 27 times. Then after that, the calculations for the areas of the broken down base and tier 0 components are summed up to get 7,563.6 meters squared for the base and 2,820.5 meters squared for the tier 0, which will be multiplied by the percentage 3.6 and reduced by that with each subsequent tier. Now, after these are done, the weight can pretty much be calculated by taking the gravity times the area and lengths of each tier and the densities of concrete, steel, and glass, then subsequently adding them together. The areas of the glass and the steel are a fraction of the structure's area, primarily because the glass only makes up the windows, which is pretty much only the outer edge, and they're most likely only a few inches thick. So there's that, and then the steel makes up the rebar structure of the building that is encased within the cement, so it's not a huge amount, but it's far more than the glass. Then after all the weights are calculated, we can add them together to get the total weight, and then such can be divided by the area of the base in order to get a stress of 1,320.31 psi exerted from the building. Then the strength of the C80 concrete can then be divided by this to get a safety factor of about 5.9 or about 6. So honestly, I'm pretty surprised that the calculation managed to mimic at least or support the real world result. Mainly because I believe the fact that I had not accounted for space for the floors meant that the building weight was being calculated as if it was a giant slab of concrete just shooting up into the sky. Also, the area of the spire was a bit like beefy, so that means that it probably would have had more weight to it just because of the increased area. But it is possible that my errors could have actually steered me to have this be correct or be on supporting side, just because I might not have factored in enough area for the glass and steel, making it lighter, and the area simplifications for the base could have made it bigger, and the subsequent areas of the tower smaller, just because, since the area was actually way less than the real overall area of the building, which was pretty much, I think, about 300,000 meters squared, where I think I only got about 100,000. I also could have just simply overestimated the concrete's material properties. But moving on, now we can actually talk about the tower cranes. So these machines are very tall, and can actually erect skyscrapers just like the Burj Khalifa, and kind of grow with them by being supported and kind of attaching to them. But as you can see by the diagram on the right, it has a tower, a jib, a counterweight, a counter jib, and a suspended hook block, which these are pretty much the most important parts as far as our calculations go. It also operates with a limit switch to determine the weight limit of the machine at a given distance down the jib. But even though we know this, we can still ask the question of how these tall, slender machines can keep from bending or falling over just due to the lifted load, or even just the existence of the counterweight constantly being on the back. But this can be answered pretty easily, if I'm being honest. We'll give an example to just show how easy it is. So the limit switch is broken, and an engineer must pick up a load of about 30 meters from the tower. This engineer believes that the load must be a maximum of 10,100 kilograms at this distance, if the carry weight capacity is about 300,000 kilograms or kilogram meters. If the counterweight of the tower crane is 16,300 kilograms at 20 meters from the tower, will the tower fall or bend? And we're also going to ignore the weight of the arms just because I believe that the limit switch already accounts for this, usually. This is actually solved pretty simply by converting the masses of the weights to newtons by multiplying them times gravity, then utilizing the moment and line of action from the rotational forces unit to determine that if you bring down the weights to the same height as the point A, they're only about 20 and 30 meters away. So we can use that information to calculate the moments of each weight, then find the summation of said moments, and then finding that the tower should have bent or fallen over clockwise just due to the weight of the counterweight. But since the counterweight actually is a mobile adjustable unit for tower cranes, it can be moved along closer to the tower itself or farther away, which means that I would like to pretty much find the distance that the operator has to move it just to cause the moment to be zero and for the tower to stay upright. So if we take the summation of forces again, but make the distance of the counterweight unknown, and removing the moment about A, we find that the distance should be about 18.59 meters. And an additional little fun calculation we can make, just because it's also important, is determining the diameter that the cable should be that's holding the weight, so that it can actually, withstand it. This can be done quite simply by cutting the wires and then summing the forces in the y-axis, then using the resulting force exerted on the cable as well as the strength of steel for the wire within the stress equation to determine the diameter, which ends up being about 1.7048 times 10 to the negative fourth in meters, just because obviously it's only going to be most likely a few inches in diameter, maybe 2 or 3, just as a spitball. So as far as this question solution goes, the calculations were pretty simplistic, with the answer to the question being simply that the counterweight, the limit switch, and adjustability of the weight make sure to cancel out any moment. Although it can be said that since the machine has a capacity of 300 ton meters, the cable would have to most likely need the ability to hold a maximum of 300 tons, rather than only 10,100 kilograms, just because that's obviously at a distance. It doesn't have to factor in personally the distance for itself. But so anyway, that's the end, and I hope you enjoyed. So goodbye.